Well, how are you doing? Okay, I wasn't expecting to be making another video on the dip correction because I made several in the past, and I showed how it can't work on a globe, etc. Right? But people are not paying enough attention to this, right? So I'm going to make this video, and hopefully this one will cause people to pay attention, right? Because the dip correction in celestial navigation is impossible if we lived on a globe. I'm going to show why. Okay, so we're starting here. This is Metabunk, right? Curve calculator. Distance doesn't matter, right? You just want viewer height in feet, right? 51 feet. So if your eye height is 51 feet, right, the dip to the horizon, right, is 12 minutes 7 seconds, right? 0.127 degrees, right? So that's what it's going to be for a globe because it's to the globe's geometric horizon. Now, what you're going to have is people on the opposing side screaming about, oh, you didn't add in refraction, right? But they don't have refraction. What they have is a mathematical changing in the size of their globe, right? But I'll add in just 7 over 6r for the sake of this argument. So their refracted horizon with just 7 over 6r is 0.117 degrees or 11 minutes 7 seconds. So just once more, so their geometric dip is 12 minutes 7 seconds, and their over 6 or 7 over 6r dip is 11 minutes 7 seconds, right? Now, if we go to the dip table, right, height of y here, you have height of y correction. There's the dip altitude correction tables, right? So, and we come down to 51 feet. We have, I'll make it a bit bigger. 1 second now, make it as big as possible so everyone can see it. So 51 feet is 7 minutes, 0 seconds. So for 51 feet, you're talking 7 minutes, 6.9 to 7 minutes of correction. So once again, for the globe, right, the geometric dip is 0.127 degrees or 12 minutes 7 seconds. Their over 7 over 6r dip is, not that I should have to add this in because it's a little rubbish, has not to do with refraction, but I'll throw it in anyway just to keep people quiet, is 11 minutes 7 seconds. So the problem is that none of them match the actual celestial navigation dip correction, right? And the reason they don't is because this correction here is too horizontal. It's not a correction to an horizon that is below the horizontal from the water underneath the boat. This is correcting to a horizontal. That's the whole point of it. Whereas if we go back to here, let's go to this 7 over 6r dip, right? As we know from observations like the black swan and all the rest of it, the horizon is often way further away than it would ever even get close to conforming to a geometric globe. And within their model, the horizon is always at least, right? Their globe is always at least refracted to the rate of 7 over 6r, which means that this here doesn't exist, right? This is pure calculation, right? Well, it's all pure calculation, but that's not the point. The point is that their horizon is always constantly refracted. So the real black swan would be a geometric horizon, because all horizons are white swans. There is no way out of that, because even within their model, they must claim a consistently refracted horizon. And the reason is because the horizon gets closer and moves further away, gets closer, moves further away, because it's an optical phenomenon. So they must claim optical phenomenon, right, via their atmosphere, right, to account for what doesn't show up, which is this geometric nonsense, right? There is no geometric horizon, there is no geometric dip. It's total nonsense. But, right, this is what their model is, right? This is what they must claim. So, but for the purpose of this, To do the dip correction on the globe, right? What they would need to have is the distance to the horizon within the nautical almanac, because this is 7/6R, right? Now this is from a 1 foot observation height. Or sorry, this is a 51 foot observation height, but 7/6R is 7/6R is what it does is it changes the distance to the horizon. So that distance doesn't matter if it's an arc distance or horizontal distance. The point is that it changes the distance, right? So the distance to the horizon from 1 foot or any other observation height will never match their geometric globe. It will always be some derivative of over 6R, right? And as I showed before, with the likes of BLMS B69's 31 mile away observation from 1 foot at Santa Barbara, they needed to claim 3,845 over 6R. You know, it gets into absolute crazy ridiculousness. But the point is that they need to know the distance, right? This is important. So, because for them to know, right, how much dip they need to know the distance to the horizon. Now, the distance to the horizon is not possible to know. If you've ever been at sea, I have been, right? And now, when I say at sea, I wasn't a merchant seaman, but I've been several miles away from the shore many times. And when you can't see land, the land becomes too small to see. When you can't see the land, you're so far away. And all you see around you is sea. Or even if you just look away from the land out to where there is only sea, there is no way to tell how far away the horizon is. So what they need is a situation where there's a nautical almanac that somehow magically changes from minute to minute. That it's somehow being rewritten by God Himself, constantly telling you how far away your over 6R horizon is, because that's what they need to do dip correction, because they need to know a distance to know how much over 6R they need to have, right? It's total nonsense, right? But that's what they need. So whereas in reality, the dip is just height of eye correction. That's what it is in reality. And in reality, 51 feet is a 7 minute correction, right? Whereas on the globe, right, it's either sorry, on the globe, it's either a geometric 12 minutes 7 seconds correction or 7/6R 11 minutes 7 seconds correction, right? So they don't match, right, what's going on in celestial navigation. So just want to read out here. So I'm just going to go through. Sorry, that wasn't the one I meant to put up. That'll do. And I'm going to go 1 second now. I just want to put in. Now, I have to read out. I have that one. Get that. Right. I have to read out. It's about the height of eye correction. Right. 1 second. Now, I'm not mixing myself up. Right. Here we go. Okay. So I'm going to read out some citation for the dip correction. Right. The next error to correct for is height of eye. The tables all assume a height of eye of exactly 0 feet. That is because then the horizon is at a 90-degree angle to the zenith. Right? The diagram above shows an exaggerated picture of the change in the HS based on the change of the height of the eye. Your height of eye is your sextant's distance, right? This is important. Is your sextant's distance above water level at the time of the sight, right? To determine the correction for height of eye, use the dip table on the inside front cover of the nautical almanac. Notice that the dip correction is always negative. The dip table is a critical table. This means that you must find two numbers that bracket your height of eye. For example, if your height of eye is 10 feet, we would go down the column labeled feet on the right of the side of the table until we find a number larger than 10 feet. Here is 10.5. Now move to the left, and there is a correction placed midway between 9.8 and 10.5. Right. So this is what dip correction is. It's your height of eye is measured at port before you leave. That's where it's measured at port before you leave. So you know, and it's measured. It's measured with either a full load or an empty. Whether it's full or empty, it's going to be measured. So the navigator knows what their exact height of eye is, and it's measured with a tape measure at port. Right? Anyone who's been at sea will understand you can't measure Even with a tape measure out at sea, because it's going to be as rough, you don't know how rough it's going to be. So you can't trust that at the time. You must do it at port and the calmest weather you can find, because at port is always calmer than outside of port, right? So they do it there and then at port. And that's where if they're going to have a lot of weight inside the boat, then at port is where the most of it would be, right? So they have to take that into account too. So that's what they do. They measure it at port, and they then subtract it every single time that navigator does a sighting of a celestial body. They will always subtract their height of eye from that. So they're bringing their eye to the water, right? Now, it doesn't matter if you bring your eye line in the vertex of the angle to the water below you. You can also describe it as the line coming up to the eye line. And this is where our opposition get very confused, because they think that the line coming up is coming up from a globe's horizon, and they think that that's what they're correcting for. But I've just shown that's not what you're correcting for. You're not correcting for that. You're correcting from a horizontal up to it's a differential between two horizontals. So it's a vertical correction. And it doesn't matter, as I said, if the vertex of the angle goes down to sea level, as is always described, or you can take the line that's going from the eye line to the horizon and bring that up the eye line. The correction is the same amount, which I will show in a while anyway. But it's the same amount of correction. Okay, so the next citation. The next thing we must account for is the fact that the horizon we see is not really 90 degrees from our zenith or from the vertical, unless our eye is right at sea level. Once again, sea level. At sea level, the horizon is tangent to the sea surface and at right angles to the vertical. But our height of eye gets higher, the visible horizon. But as our height of eye gets higher, the visible horizon dips lower and lower. Excuse me. The higher our eye, the bigger the amount of this dip angle. Right. Figure 13.3 illustrates the situation. Dip is purely a function of our height of eye. So if that height is known, dip can be calculated. Right. So next one. Cool. Right. Dip. The altitude of the sun, which we measure above the observer's horizon, is always too high, and this dip error always needs to be subtracted, hence the sign in front of it, right, figure 2.6. This is because the observer is standing on the deck of the boat, and thus well above the surface of the ocean when taking a second sight. As a result, our observer's horizon is further away and lower than the rational horizon, which we would use if our eye was just above water. For instance, if we were looking at the horizon from the periscope of a submarine, right? The higher the observer is above the surface of the ocean, the larger the dip. Right, so here we have, over here, observer's horizon, geoidal horizon, sorry. The nautical almanac and the site reduction tables assume that the sites are taken at sea level, for instance, from the periscope of a submarine barely emerging above the water, right? Height of the observer's eye above sea level determines the dip. This angle must be removed from the altitude of the celestial body above the altitude of the celestial body above the horizon that is measured with a sextant. H sextant to obtain the apparent altitude HA. See, they're not saying it's the height of the eye above the horizon, it's the height of the eye above the water underneath the boat. Now, what the globe needed, our opposition need is they need it to be for an angle from their globe's horizon up to the eye. But they need their horizon is constantly refracted, right? According to them, right? Which means that there's no telling how far away it is, so they could never know how much over 6R to add. And anyway, it wouldn't matter because none of that happens in reality, right? I showed the values earlier, right? For 51 feet, it's 7 minutes of a change, right? Whereas on their globe, it's 12 minutes, 7 seconds. Or if you want to add in over 6R, 7 over 6, or it's going to be 11 minutes, 7 seconds. But to even add in 7 over 6R, they need to know how far away that horizon is matching 7 over 6R as a distance. It's total nonsense. There's no distance to horizon part in almanacs that can tell you the distance to the horizon. It's impossible to know. Anyone who's been out to sea will tell you it's impossible to know how far away the horizon is at any one time. So here we are, a summary of dip angles, various heights of observation above sea level, right, in meters and feet, right, dip angle. When there's 0 meters, 0 feet, you have 0 dip angle. It's that simple, right? That's very obvious. Okay, height of y. The height of y over the surface of the water in feet or meters. The site reduction tables used for a site with a sextant assume the eye to be at ocean level. In the general case, and because of the height of the eye above sea level, the angle measured with a sextant HS is a little too high, since the actual horizon seen by the observer is a little further away, and therefore a little below the rational horizon at the edge of the horizontal plane. The angle HS measured with the sextant therefore needs to be corrected for the dip, the small angle between the horizontal plane, rational horizon, and the actual horizon. Right? So what they're saying there is site reduction tables always place the eye at sea level. Right? The almanac and site reduction tables always place the eye at sea level. That's what it does, because it's using sea level as its horizontal. It doesn't matter if people want to describe it as the line coming up and they're making a parallel, right? The line coming up from the horizon to the eye, because it's the same amount of correction. It doesn't match a globe, it only matches a horizontal. It only matches mean sea level being a horizontal, because it doesn't matter if you're making a parallel with another horizontal line that's parallel with the horizontal mean sea level, or you're using mean sea level as your horizontal. It makes no difference. The point is that it's the same correction, right? Which we're going to get to in a minute. Okay, so this is just because I have to throw in these next two citations here, because they're kind of a lucky dip for people, or an extra, because we often get from our opposition, you need to know the height of a celestial body, because it's a total straw man. What they're trying to straw man us with trigonometry, when we're not claiming trigonometry, we're claiming triangulation, because that's what celestial navigation does. Nobody claims the height of the celestial bodies in celestial navigation. But of course, our opposition are trying to hijack celestial navigation, even though they can't even do dip correction. It's pathetic. But anyway, that's what they do. But these two, I have another two citations on this, but just two is enough. Altitude or elevation. These are synonyms for the angular height of an object above your horizon at any given moment. When a star is on your horizon, so that it is either just rising or just setting, its altitude or elevation is 0. And when it is directly overhead at the zenith, its altitude or elevation is 90 degrees. Keep in mind, this is important part, keep in mind that this is an angle, not a physical distance, right? So they're not claiming a physical distance, just an angle, right? Smithsonian, right? A sextant is used to measure the altitude of a celestial body above a horizontal line of reference. Altitude in this case is a special use of the word describing an angular measure, not a distance in feet above sea level, right? A mariner can use the horizon as this line of reference, but when an airplane is above the clouds or flying at night, its navigator can't see the horizon. The bubble sextant solves this problem by providing an artificial horizon. It takes its name from an air bubble in a liquid-filled chamber that functions like a carpenter's level, indicating when the sextant is aligned horizontally. So level is horizontal. When I look through the eyepiece of my sextant, I locate a star, and with a drum on the side of the instrument, like a camera's focus ring, adjust the angle of a rotatable prism until the star showing in the eyepiece is aligned beside the bubble. The prism and drum are geared to circular scales marked off in degrees. From these scales, I read the star's altitude. So altitude, in this case, is a special use of the word describing an angular measure, not a distance in feet above sea level. Nobody is claiming a height of celestial bodies. Nobody who's a flat earther is claiming them, that's for sure. Or any flat earther that's worth their salt, because there seems to be a lot of stupid flat earthers out there. Okay, so this is the coup de grace, right? Back to what we originally spoke about. So here we are. Where are we? Sorry, where's it going to? Oh, it's behind that, right? So here, right, 51 feet, your height in feet is 12 minutes 7 seconds. If you want to add in, if they knew how far away the horizon was, right, magically with their psychic powers, and it was 7/6, which is the least it can be, because it's always claimed to always be refracted, is 11 minutes 7 seconds, right? But in reality, 51 feet is 7 minutes. That's it. 7 minutes of a correction. That's your correction. 7 minutes. That's it, right? And the reason is this, right? This here, this is 50. So this is just off of GeoGebra. The scale is a bit out, I understand that, but I have to be able to show it, right? So this is 50, right, on GeoGebra, right? So when I come across here, this is still 50. But when the angle down to a globe's horizon down here, when I bring that angle down there, then that line there is 95. Now, as I said, the scale's a bit out, but the point is the same, right? That 50, right, a height of y of 50, right, can't be accounting for 95. That's the point, right? So height of y, 50 feet, globe's dip correction, 95.79 feet, leaving a deficit of 47.79 feet not corrected for. The point I'm making here, as I said, it's not 100% the scale. The point I'm making is their corrections, their dip corrections, not only would they need to know how far away the horizon is, but they also then, their dip corrections aren't going to work because they're going to have an accumulation. So every time, because every time they're doing a sighting, they're going to be doing more than likely 3 circles of equal latitude. That would be 3 sightings. So if a navigator is doing several sightings a day, or even just a couple of sightings a day, over the course of, let's say, I don't know, maybe a month of travel, a couple of weeks of travel, depends if they're going from somewhere like London to, I don't know, somewhere in Florida, South America, something like that, I don't know by how long they take. But the point is that all those sightings, right, all those times that they didn't have 90 degrees at the observer and 90 degrees at the GP, right, will mean that they've always had more than 90 degrees at the observer and less than 90 degrees at the GP, which means they would, now, they can't have 90 degrees, I understand that, but the point is that that would be an accumulation where they will end up being hundreds, maybe more than hundreds of miles away from where they intend on being, right? This is the problem. It doesn't work. Dip correction doesn't work on a globe. And all I have to do is show, once again, they're at Metabunk, 51 feet. The dip is 12 minutes, 7 seconds. And even for our 7/6R, which there's always at least 7/6R, right, according to them, it's going to be 11 minutes, 7 seconds. But in reality, it's just 7 minutes. That's it. So that's the end of that. I'm going to stop it there now. I think I've shown all the things I need to show. None of this works on a globe. Anything they want to talk about always has to start at, if they want to talk about celestial navigation, they always want to get past all these points. These are the things that stop it. Now, I could go on and take apart the Universal Transverse Mercator map, which is what they place the circles of equal altitude on, which, because the Universal Transverse Mercator map is a globe projection, it instantly mutates the original measurements. And then they use the Haversine to turn that back into a globe, which mutates it even more. And the whole thing ends up just being a big mathematical begging the question fallacy, right? That's the problem. But so all that doesn't matter. What matters is the actual measurements and things like dip correction, especially dip correction, because it proves that level is horizontal. Dip correction proves level is horizontal. Level can't be not horizontal if this is sea level, because you could only have 50 foot to correct for, so you can only correct for 50 foot. Doesn't matter how far away the horizon is, you can only correct for 50 foot. Right? That's that. You can't do this with a tangent plane. You can't do this with a curved surface. There's no way out of it. Dip correction, it ends right there. All globe claims concerning celestial navigation end right here, because they can't get past this point. And this is other than index correction, a couple of small things with the sextant itself, this is the correction they need for the measurement to happen. And for that to happen, they need 290 degrees, one at the observer and one at the GP point, with a horizontal baseline between them. But they want to try and put in a tangent plane, not do dip correction, take an angle, ignoring dip correction, and then bring that tangent plane angle down to the center of their globe and use their equatorial plane. That's what they try to do. It's totally fraudulent, but that's what they try to do. Let's pretend none of that. Let's pretend dip correction doesn't exist. Let's pretend dip correction didn't happen. That's what it is. Boo, dip correction. That's what it is. You know what I mean? It's like the sheet over with the ghost with the chains and the sheet and woo, dip correction. Because they can't do dip correction. So that means celestial navigation can't work on the globe. It's that simple. It can't be done. It's only crazy to think it can. I'm sorry, it's over. That's the end of that. Thanks for watching.